Hi, welcome to this video. We'll see an example of how to calculate shear stresses due to torques or twisting moments in shafts. So we have here a shaft that's supported by bearings at A and E. So E here is shown to the right of the shaft. And the shaft has this radius of 0.75 inches. And supports these three torque twisting moments at B, C, and D. The member has a section or a cut section somewhere between C and D, and actually it doesn't matter that much. We'll see the torque in this distance C and D is the same, but we'll do the statics in a moment. And we need to determine now the shear stress tau now within this section. If we zoom in, we'll find that there are 2 points of interest here, A and B. A is at the outer radius of 0.75, and B is at a little closer to the center, away 0.15 radius from the centroid. So the first thing you do is analyze the statics and equilibrium of that cut, and what we will do here is we'll analyze the left part of it. So we'll see the part that has the B and C loads, and when you cut at this section somewhere between C and D, we will reveal here the main action that's happening internally is the torque. So we don't have a normal force or shear force. It's mainly pure torque action here. And I will analyze here the equilibrium to figure out what is the value of this internal torque, and I will assume that positive direction here as shown. So I'm assuming there's the axis going out of the section, and using my other right hand rule to figure out the positive moment or torque around this axis. My thumb is pointing to the positive of the axis, and the rest of my hand is rotating around my thumb. That's the positive direction of the moment. So I'm considering that's my positive, and if I do the sum of the torques or the sum of moments around this axis, I will figure out that TCD is equal to 12.5 kip inches. TCD is a torque internal at any point between the distance or point C and D. So if I cut it a little to the right or cut it a little to the left, it will always be equal to 12.5 kip inch. Next would be now considering the cross-sectional stresses due to the shear stresses due to the torque, and we know from the previous section that shear stress is dependent on the polar moment of inertia. So J here we need to calculate it, and just considering the radius, that will be 0.4. The J will be 0.497 inch to the power 4. We need now to see what are the stresses at this section CD, and using the formula here for the torque, T rho over J. That's the general formula for the shear stress from torque. And I'm interested into the first point here, A. So if we apply the formula, rho here is equal to C, because A is at outside or the outer perimeter of the section, and B is at 0.15 inches from the centroid. So applying the formula, just to have all the values, just apply them. I will figure out that tau at A is equal to 18.9 ksi. All my units here are kips, kilopounds, are in inches. Now let's pause here a little before moving to tau B calculations, and really see where this tau A is acting, meaning the direction of it. I know it's acting at A, but is it acting right, left, up, down? So if we kind of zoom in, and if I draw this radius between the centroid and A, and then imagine this is my pen, and this is the line from the centroid to A. My pen is pointing to the direction of the torque and going. I think I'm following the direction that you'll have in your screen. But regardless if the moment of the torque is going this way, my pin will be pointing the same direction of the torque, and this is the line, this is the radius. So the torque will cause shear stresses in this way, in this direction. So TA will have tau A, the torque at A, will follow a direction tangent to the torque direction at A. And if I take a block representing point A, and that face I see in front of me, where the arrow is drawn, is the same face of the cut I have, CD. So the torque now will be going to the right, which is to the Y direction, and it's acting on the surface perpendicular to the X axis. So I will call this tau XY. Tau X, surface perpendicular to the X. Tau XY, Y here is the direction of that torque. And we also know that for equilibrium to happen at this point, there's other shear stresses developing around this block. So that's how kind of we comprehend the direction of that shear stress at point A. Tau B now, just everything is the same, but changing rho to be equal to 0.15 inches. And now I see I have reduced value for shear stress, because now I have a point closer to the centroid of the section. Now if I zoom at B, I'll find now the tangent of the torque at this point will be the direction of tau. So tau will be actually pointing down now. And if I draw the block, the stress block of the stresses at B, this tau going down means it's called now tau xz. So tau x, because it's the surface here is perpendicular to the x-axis, and by having tau going down, down is the in the line of the z-axis, so this is called now tau xz. So that was a quick example here on analyzing shear stresses in different points in the shaft due to torque loads, and using stress blocks to really dig deeper and zoom in a point and see how this shear is developing, in which direction within that surface of the cut, and relating that to the shear stresses in the other dimensions, like the longitudinal dimension. So we are in equilibrium with the shear stress developing in the transverse direction, which is the cut section here. So in next videos of this lesson, we'll discuss the idea of calculating twisting angles, which is related in some way to how shear stress develops in the shaft. Thanks for watching. Take care.